All right, today we're going to talk about force diagrams and using those force diagrams to write the sum of the forces equations. So let's recap the forces we have talked about so far. So we have talked about three what we call contact forces. So contact forces require the objects to be touching each other. The first one of those would be the normal force, which is always drawn perpendicular to the surface. And you only have that force if you have a solid surface. The second contact force we have talked about is a frictional force. That's always drawn parallel to the surface. And you must have two surfaces sliding against each other and motion or attempted motion for friction. And then the third contact force was that tension force, which you have to have a rope, a chain, a wire, something to that effect. It's always drawn in the direction of that pull. All right, so tension only pulls. You can't push things with a rope. The normal force only pushes. Okay, so when we talked about those forces as being a push or a pull or interactions between two objects, well, normal forces only push. Tension forces only pull, okay? And then we have one non-contact force. We call it a field force. And that is the gravitational force. It's always drawn from the center of one object to the center of the other object. And it is almost always there. So no matter what you're drawing a force diagram for, it usually has a force of gravity from some object. Most of our situations are going to be on Earth, so we're going to have a gravitational force from the Earth on the object, and we're going to have a gravitational force on Earth by the object. Next week, we will get more into Newton's third law and talk about those third law pairs. Okay, so force diagrams, and the steps for solving forces. We are going to be writing today, which are called the sum of the force equations. So we're going to be looking at what's called the net or overall force. Okay, so it's called a net force. But we are going to designate it in here using the sigma. So the sigma just means the sum of whatever follows it. So if I have it in front of a force, it means the sum of the forces. The I here just means however many forces you have. So if you had three forces, it would be F1 plus F2 plus F3. Notice here that we have some of the force equations for components. So your net or overall force is the vector sum of all the forces. Remember, if they are not parallel to each other, we have to look at the components. And we are going to add those components together. We will do a couple of examples in a moment. All right, first we need to talk about Newton's first law. So it's also known as the law of inertia. If we have Newton's first law, we have object that is either at rest or it's moving with constant velocity. So not all objects with balanced forces on them are at rest. They could be moving with constant velocity. This also means our net force or our sum of the forces must equal 0. So whatever forces we have acting on it must add up to 0. So the pictures are kind of small and I apologize. But if we look at the forces here, I have a negative 180 plus a 680 plus a positive 680. Well, those add up to 0. Over here, I have a positive 100. Negative 100. Whew, it's been a long day. Negative 100 plus a positive 100, again, adds up to 0. Okay? You also have balanced forces in this situation here where the person has gravity pulling down and he has an equal force from the floor pushing up on him. So this gravity force is equal to the normal force in this situation. In here you have these pushing forces that are equal to each other. And same with you sitting on the chair, the chair pushing up, okay? We're going to talk more in context of these being the balanced forces, not that one. When we talk about this interaction of the person sitting on the chair and the chair pushing up, this is actually when we're talking about Newton's third law, and we will talk about that next week. All right. Unbalanced forces is when Newton's second law applies. So Newton's second law says that the net force acting on something is equal to its mass times its acceleration. So remember that net force just means the overall force acting on it. M in the equation stands for mass, not meters. So you might want to go and add that to your table of your variables and units. We measure mass in kilograms. So the variable is M, the units are kilograms or kg, and the A is acceleration. And of course, that's measured in meters each second squared or meters each second. And A is the variable. If you're still having trouble with that, make sure you are looking at that table and you're keeping that up to date, okay? We also can write this as the sum of the forces are equal to mass times acceleration. So remember, the net force is the same as saying the sum of all the forces. Okay, so here's some examples. So you can see now I have a negative 50 newtons to the left and a positive 30 newtons to the right. So the net force here would be in the direction of the larger force, which is going to be negative, and then you add them together, so the net force there would be 20 newtons. We have another one here where we have our negative weight or gravitational force going down. We have an air resistance force going up. So again, I would add those together and I would get a sum of the forces as a negative 9 newtons because I'm adding a positive 16 to a negative 25. And we could do the same thing with the other two. And again, look at the overall net force. So in the case of this one, these two would add together to give me a positive 8 newtons to the right, minus the 3 newtons to the left. So it would be a positive 8 newtons minus 3 newtons is how we're going to practice writing it. So my overall net force would be 5 newtons, which would be a positive 5 newtons or 5 newtons to the right. All right, so steps for solving force problems. I am going to expect you to go through these problem solving steps. And if you do not, I'm going to make you go back and do that before I will answer questions on if you have it right or if you have it wrong or any of that. So the first thing you need to do is draw a force diagram. You need to draw the force diagram anytime it talks about forces or analyzing forces. I'm going to expect you to have a force diagram, even if the problem doesn't explicitly ask you to draw one, okay? You're going to use that force diagram to create your sum of the force equations. But we first need to look at, is this a Newton's first law problem or is it a Newton's second law problem? So is acceleration equal to 0 or is acceleration not equal to 0? So we're going to look for those key words like at rest or moving with constant velocity. If it says moving with constant velocity or at rest, then we know we are looking at a Newton's first law problem. If we are, and I don't know why I had a question mark there before. Sorry about that. Should have been a 0. If it says it is slowing down, if it says it is getting faster or speeding up, or it says it is accelerating, then we are looking at a Newton's second law problem. The third thing we need to do is to set our X and Y axis. This is going to be very important for analyzing these forces. The rule for the x-axis is that it should be parallel to the surface. And the rule for the y-axis is that it should be perpendicular to the surface. Okay, so once we have these axes, we're going to start looking at the forces on or parallel to the x-axis and on or parallel to the y-axis in order to write out our sum of the force equations. So let's look at some examples so this can be done in context. So this is one of the forces we did on our practice problems. If you were an in-person student, we had the ice skater moving at constant speed. If you were an at-home remote learner, then you had, I believe, a hockey player moving at constant speed. So here is our keyword here, constant speed. It also tells us frictionless, which means there are no frictional forces. So if I do the system schema, I have the skater, the ice, and the earth. I have an interaction between the skater and the earth. I have an interaction between the ice and the skater. And then I have an interaction between the ice and the earth. We are drawing a force diagram for the skater. So when I circle the skater, I see I have 2 interactions. So my force diagram should have 2 forces acting on it. The gravitational force on the skater by the earth and the normal force on the skater by the ice. Okay, so we only have one axis here. If you are solving a problem that has requires you to draw a force diagram and then do a force analysis, you would be drawing your X and Y axis on a separate force diagram. I don't have a lot of space here, so I'm going to draw it on the same one. But you would want to put this on another one. So again, our X and Y axis should be parallel and perpendicular to the surface. I only have forces along the Y axis, so I'm only going to worry about drawing that one in. But if we had forces on the X, we could also label our X axis. So now we do some of the force equations. Normally we would break it into X and Y pieces because those act independently of each other. So whatever is going on in the horizontal direction acts independently of what's going on in the vertical direction. Something that kept coming up in class is, why doesn't the ice skater have any other forces acting on her? Well, she's moving at constant speed and we have frictionless motion. So then the question was, but how is she moving? At some point, she pushed off on the ice to get herself moving. But the force diagram is for what's going on right now. So this is after she pushed herself off on the ice, and she's just coasting along on the ice at constant velocity. So again, the horizontal is not applicable to our situation. We have constant speed, which means the sum of the forces should equal to 0. We have a Newton's first law situation here. So my sum of the forces are equal to 0. My sum of the forces, and I should put a Y in here to designate we are doing vertical forces, are also equal to everything on or parallel to my x-axis here. So the normal force is going up. That's a positive force. My gravitational force is going down, which is a negative force. So my equation becomes the normal force minus the gravitational force. Okay, so now this is the part that gets confusing for students. We're going to combine these two because X is equal, or sorry, the sum of the forces are equal to 0, but they're also equal to this equation here. So I can combine those and say that 0 is equal to my normal force minus my gravitational force. So the best analogy I can give you for this one is using money. So if I had a $10 bill, I can say that that's equal to a $5 bill plus a $5 bill. I can also say my $10 bill is equal to 10 $1 bills. Well, since my $10 is equal to the 2 5s and my $10 is also equal to the 10 1s, that means my $5 bills that I add together are also equal to the 10 1s. And I am not going to draw 10 more 1s out here. You get the idea. Okay? The equal sign in equation means that this is the same as the other side. So if this is equal to that side, but it's also equal to this, then that makes these two equal to each other, which is exactly what I did here with these forces. Now I can add my gravitational force to both sides. And so for the ice skater, my gravitational force is equal to my normal force. Okay, let's look at another one. All right, the ball. This is another one that students had a few questions with. Do that system schema. It helps you. The ball pulls on the earth pulls back on the ball. I am drawing a force diagram for the ball. So my force diagram is just going to have the gravitational force on it. And that's going to be by Earth. Oops, I don't know what I did there. Okay, by Earth. So now I can do my axes. There's my y-axis. I don't have anything going on in the horizontal direction, so I don't need to worry about it. Oh, let me make that a little bit different. There we go. So again, I don't have anything in my horizontal direction for this one, so I don't need to worry about it. In my vertical direction, I now need to decide if this is balanced or unbalanced. Well, I can look at this force diagram right here and see that I only have this force going down. So this is an unbalanced situation or a Newton's second law situation. So that means the sum of my forces are going to be equal to the mass of the ball times its acceleration. The sum of the forces are also going to be equal to just the gravitational force. That's the only force I have on or parallel to this y-axis. So that means now, since the sum of the vertical forces are equal to the mass times acceleration, but the sum of the vertical forces are also equal to the gravitational force, that the gravitational force must equal the mass times my the mass times the acceleration. And I have now written my equation I can use to solve for any of these three pieces of information. All right, let's look at one more. So now we had those forces at an angle. So we had the squirrel, we had the roof, and of course they are both on Earth. And the squirrel pulls on Earth, Earth pulls back on the squirrel. The squirrel actually has two interactions with the Earth, a supporting interaction, and then in order for this squirrel to sit still, we must have a rough surface. If we have a rough surface, we have friction. So we have two interactions from the roof. So let's draw our force diagram. So let me draw it over a little bit because I need to have room to draw some of the force equations. Okay, gravitational force on the squirrel by Earth. Then we have a solid surface. Normal force rule is that it is perpendicular to the surface. So it is like that. Well, if I look at this, I can just kind of see that this is tilted to the left, which would mean that the squirrel would tend to slide down the roof, but something must be holding him up. So that is a frictional force on the squirrel by the roof. And I forgot to put the normal force is on the squirrel by the roof. So there's two interactions going on with the roof here. I'm going to go to a clean slide to analyze this because I am not going to have enough space here. Okay, so here's my force diagram for the squirrel. The squirrel was at rest, so I have a Newton's first law situation. Acceleration is equal to 0. So when I do my sum of the force equations, I need to first do my x and y axis. So the rule is that the y-axis is perpendicular to the surface. That means it'll go along my normal force. And the frictional force is parallel to the surface, the x-axis is parallel to the surface, which means it's going to go along my frictional force. Because my frictional force is always drawn parallel to the surface, and my normal force is always drawn perpendicular to the surface. All right, I want to go back and show you one thing in the picture. For the picture, we have our angle, which would be down here. I kind of made a mess over here. There would be my angle relative to the horizontal. So I'm going to show you where this angle ends up on your force diagram. So I have my roof and I have my angle. I'm just going to do a box for the squirrel. So I'm going to go ahead and draw the normal force going up, the gravitational force going down. So I ran my y-axis along this normal force. So I can see I have some triangles here, some right triangles. I have a right triangle here. So this is my 90-degree angle. That means this angle right here has to be 90 minus theta. I have a right angle here and another right triangle there, which means we also have a 90-degree angle between those two pieces right there. So if this half of the angle is 90 minus theta, then that means this half has to be theta because that has to add up to 90. So let's talk about that in reference to our force diagram. That means our angle theta is right here between the y-axis and the gravitational force. So you can see my gravitational force is not on my x or y axis. So the gravitational force is the one we're going to break into x and y components. That means I have a vertical component of my gravitational force that goes along that y-axis, points downward. And then I have a horizontal component that goes parallel to the x-axis and to the left down the roof. There is my 90-degree angle. So that makes this force right here my hypotenuse. Okay, the reason we break that force into components is because we have a way to quantify that force. And we'll talk about that as we go through an example on the next, on the practice problems. I'll go ahead. Oh, no, I'm not going to write it here. We'll worry about that equation in a minute. All right, so my table to analyze my forces and do the sum of the forces. I need to use x and y separately. So in the horizontal direction, we already said our overall acceleration is 0. So the sum of the forces in the x direction should equal 0. The sum of the forces in the x direction are also equal to everything on or parallel to my x-axis. So that is my frictional force going up the ramp minus my horizontal component of gravity that is directed down the ramp. So just like before, I can set those equal to each other. This equation is equal to the second equation. So I have my frictional force minus that horizontal component of gravity are equal to 0. I can add that horizontal component of gravity to both sides. And I can see that my frictional force is equal to that horizontal component of gravity going down the ramp. I can do the same thing in the vertical direction. Again, it's all equal to 0. It is also equal to everything on my y-axis. I have no forces parallel. So I get the normal force minus that gravitational force, because that's my positive, that's my negative. Here, that was my positive, and that was my negative. So I can set that equal to the first equation, because these are the same expression. I can add that vertical component to both sides, and I find that my normal force is equal to that vertical component of gravity. All right, let's look at one where the surface is not tilted. Oh, sorry. Let me go find it. Here it is. All right. Force diagram should have been the gravitational force that's acting down on the sled. Sled interacts with the rope. The rope interacts with the person. So we call that a force of tension. The normal force is perpendicular to the surface. And then it doesn't tell us if it is at constant velocity or if it is accelerating. So I could leave my force diagram like this, or I could assume the snow is a little rough and I could have a frictional force going to the left. So let me draw this on a new slide. Quickly before I move on, that tension force is always drawn in the direction of that pull. So it's always going to be in the direction of the string. So this one's at an angle. So it's on an angle on our force diagram. All right, so here's my diagram. I'm going to draw in my X and Y axes. My angle is right here. So I can see that this tension has a horizontal piece going to the right, and it has a vertical piece going up. So split up my horizontal and my vertical. I cannot add a horizontal force to a vertical force directly. I have to use trig, or I have to use Pythagorean theorem. Let's go ahead and assume it's equal to 0. So we'll say that the acceleration is equal to 0 in both directions. Then I need to add together everything on or parallel to my x-axis. So I would have the horizontal component of the tension minus the friction. I'm just getting that from my diagram, which means my horizontal component minus my friction must equal 0. Add the frictional force to both sides. And my tension must equal my frictional force. I'm going to do the same thing for the vertical. Sum of the forces are equal to 0. This is not, sled's not floating up off the ground or falling down through it. It's also equal to that vertical component right here, plus the normal force, because it's everything on or parallel to the y-axis, minus everything going down, which is the gravitational force. Sorry. All right, that means my vertical component of tension plus my normal force minus my gravitational force is all equal to 0. So then I can solve for any of these three things, but it tells us everything going up, because I have balanced forces, must equal everything going down, because I can move this to the other side by adding it to both sides of my equation, and I get that for my final expression. So let's look at some examples with numbers. That video will be included with the packet of practice problems, which is in the next part of this module. Have a great day.